Hello everyone, today we'll make a discussion on Walsh diagram. So to know Walsh diagram, we must need the knowledge of B.Sc pair theory, MOT and group theory. However, today we will discuss about only the Walsh diagram. The B.Sc pair theory, MOT and group theory we will discuss in next lectures. So now let's discuss about Walsh diagram. It was given by A.T. Walsh in 1953. It is otherwise known as angular coordinate diagram or correlation diagram, as it correlates both bond angle and molecular geometry of the orbital energy. There are certain rules to draw the Walsh diagram of a molecule. So let us discuss all these rules. So it is rule number 1. The limiting structure of the molecule should be calculated. It is rule number 1. The limiting structure of the molecule should be calculated. For example, if you take the example of a triatom molecule, there are two possible geometries, that is linear geometry and bent, right? Then come to rule number 2. The point group of the molecule should be determined. So for bent geometry, the point group will be C2b, and for linear geometry, the point group will be D infinite H. Then rule number 3. The coordinate assignment of the molecule should be determined. For non-linear molecules, the principal axis should be Z-axis. Then rule number 4. The character table of irreducible representations or the possible point group should be derived. Rule number 5. The irreducible representations as per the symmetry of the group orbital and central atom should be derived. Rule number 6. The atomic orbitals of central atom with same symmetry should be same. Rule number 7. The MO diagram can be drawn by combining the AO of the central atom with the LGO of the peripheral atoms. Then come to rule number 8. Correlate the energy of the molecular orbital of the limiting structures. Rule number 9. Inner orbital, that is 1s, will not include in the Walsh diagram since their energy does not change much by bond angle bending. Rule number 10. Similarly, the MO structure can be drawn for the compared point group. And rule number 11. Walsh diagram can be drawn by comparing the two MO diagram to get confirmation regarding the correct one. Now let will discuss by taking some examples. Here it is the first example, the simplest example, that is H2 molecule. Here you know that in H2 molecule, two hydrogen are there. So this is atomic orbital 1 hydrogen, this is atomic orbital 1 another hydrogen. So they will combine to form the molecular orbital. One is bonding and one is antibonding. This is the simplest structure. Now come discuss about BeH₂ molecule. It is a polynuclear molecule, and you know that in polynuclear molecule there is a central atom and there is a peripheral or side atom. So here the rule number 1 is the peripheral atom will combine to form the group orbitals, that is GO, right? The peripheral means two hydrogen will combine. So this is two hydrogen will combine to form group orbitals. So if two hydrogen, one is orbital of two hydrogen will combine, there will be two possibility. So one is in phase, means constructive overlapping, bonding, and one is out of phase, that is destructive overlapping, that is anti-bonding, and one node is present in anti-bonding, right? So it will be sigma G and it will be sigma U. It is a LGO, means two peripheral atom will combine to form two LGO. One is bonding, another is anti-bonding. So what is the difference here between the two? Here two atomic orbital will form the MO, and here the LGO and the atomic orbital will form the MO, right? So this is the first rule that we have to know to draw the Walsh diagram. So now we will take the example of water. It is a very important example. It is a triatom molecule. So rule number 1, possible geometry is to linear and bent. Rule number 2, point group. For bent, point group will be C2b, and for linear, point group will be D infinite H. So rule number 3, Z-axis is the principal axis. There is Z-axis is the principal axis. Rule number 4, character table of irreducible representations for the possible combinations of the valence orbital of the surrounding atom. See here, the important point here is here I will not discuss about how the character table of C2b will be like this. It will be discussed in the group theory only. But here you have to keep in memory that this is the character table for C2b point group, right? Here I can tell you one shortcut trick how you have to keep in mind the table completely. So here see, Here it is C2 point group. Here it will be A1, A2, B1, B2. So 1, 1, 1, 1. Here it is 1, 1, 1, 1. And the diagonal will be 1, 1, 1, 1. Rest are only minus 1. So this is the trick to memorize this C2B character table. Then S5 problem 5, the irreducible representations of LGO and CS would be derived. So here we have two atoms, one is central atom, one is peripheral atom. So for central atom, see for central atom, in central atom 2s is there because 1s will not participate, and so 2s is there and 2px, 2py and 2pz are there, and it will be derived. Okay, this will be derived, and the irreducible representatives will be A1, B1, B2 and A1. See here the important point here you have to know is for a molecule we have to use the capital A1, A2, B1, B2 capital signs, but for LGO and atomic orbitals we have to use small letters A1, B1, B2, A1, and here A1, B2. Okay, and here we know that for hydrogen 2 LGO was there, one is bonding, one is anti-bonding. So how can you memorize these things? See, you have to only keep in mind this one only, means for 2s the irreducible representations will be A1. For 2px it will be B1. For 2py it will be B2. For 2pz it will be A1. And accordingly you have to write it from here. Here the value of A1, A2, B1, B2, you have to only put it here. Value of A1, this value of B1, value of B2, value of A1. Okay. Similarly for hydrogen, it will be A1 and B2. Okay. So I think it will be easy to memorize. So now symmetry allowed orbital combinations between hydrogen LGO and oxygen AO for angular H2O. See here what we have to do, we have to compare for both C2B and D infinite H. So here I have drawn it for first C2B. So here SLs means symmetry adapted linear combination. Symmetry adapted linear combination. And here it is AO, atomic orbital, level and molecular orbitals, right? So see what is important here is, see here 2s is spherical in nature, so it can be combined with this LGO of hydrogen, and here there is two possibility. 2s may form bonding or may form antibonding with this LGO of hydrogen. So the structure will be, if the bonding, the structure will be like this. If it will form antibonding, the structure will be like this. And see here what important here is for 2s it is A1 and the hydrogen A1 is also there. We have already discussed. See here 2s A1 and hydrogen A1, right? So the structure will be like this. So symmetry adopted linear combination, as symmetry is there, so they will combine. For symmetry because it is A1 and for 2s it is A1, so symmetry is there, they will combine. But here 2px is B1, so here you can see that here B1 is absent. So here combination usually will not happen. So it is, I just put cross mark here. Okay, and 2py is B2. See, B2 is present here, right? So possible combination is possible here, right? And one is similar, one will form bonding and one will form anti-bonding. And for 2pz it is A1 also, for 2pz A1 and A1 is also present in LGO of hydrogen. So combination is possible here. I think it is clear to all of you. So here I have drawn the structure, molecular orbital structure of C2B point group of water molecule. Let check it. See, this is your 2s, it is A1, it is 2px, 2py, 2pz, it is A1, B1, B2. See here I have write the energy only, right? And the energy of LGOs of hydrogen will be minus 13.6 electron volt, and it is minus 32.4 electron volt, and for 2p it will be minus 15.9 electron volt. So definitely this side is for this left side is for your oxygen and right side is for your hydrogen, right? So now come to discuss this diagram. See here it is A1 is present in 2s and it is also A1 present in LGO. However, the energy gap is too large. See the energy 13.6, 32.4 energy gap is too large. So only because of this reason, this will be remain as non-bonding, right? Only because of high energy gap, this will be remain as non-bonding. So here, see here non-bonding having slightly bonding character because symmetry is there. Okay, slightly bonding character as well as non-bonding character because due to high energy gap, usually bonding is not possible. Okay, so here it has slightly bonding character due to symmetry. So now come to this one. See here A1, B1, B2 is there. Here A1, B2 is there. So A1 will combine with A1 and B2 will combine with B2 to form two bonding and two anti-bonding, and B1 will remain non-bonding. Right? I think now it is clear. So here this is the your LGO, this is AO, this is the MO diagram of water molecule for C2B point group, and you know the bond order will be 2 here, and which is the right actually in water bond order will be 2. Okay, and here one important thing that is you have to know that purely non-bonding or more P character. It is purely non-bonding, and it have partial bonding character and partial non-bonding character, right? Now come to the second one. We'll discuss about the linear water, that is D infinite H, right? So for D infinite H, the symmetry adapted linear combination. See, symmetry adapted linear combination for linear structure, we have to draw it like this. And here see the for 2s, the label will be sigma G plus. For 2px, it will be pi u. For 2py, it will be pi u. For 2pz, it will be sigma u plus, right? So here 2s can combine with the LGO to form molecular orbitals. One is bonding and one is anti-bonding. It is clear. And with 2px, so between 2px, 2py and 2pz, only 2pz will be in the axis. So it will form bonding and as well as non-bonding. But with 2px and 2py, it will be it can be linearly combined. So it will not form any type of bond with 2px and 2py. It will form only bond that is present on the same axis. So here only one 2p orbital will form the bonding as well as anti-bonding, right? So now this is the MO diagram of linear water molecule, that is D infinite H point group, and here it is your for oxygen side, this is here for LGO means hydrogen, H2 LGO, it is for oxygen. The same thing here, it is true that here it is sigma G plus and sigma U plus, because one bonding will form and one anti-bonding will form, so G and U. So here sigma G plus is present, here sigma G plus is present, but the same reason, due to same reason, it will be remain as non-bonding because of high energy gap, right? High energy gap 32.4, 13.6 energy gap is high, so it have partial bonding character and partial non-bonding character, right? And here it is sigma G plus pi u and pi u. It is sigma G plus and sigma u plus. So only one bonding will be formed, sigma G plus with sigma G plus, that is oxygen with LG of hydrogen. Here two non-bonding are present, pi u and pi u. Here one non-bonding is present, that is sigma u plus. Okay. So here our bond order will be 1, that is actually not true. In water, bond order can be 1, right? So this is our Walsh diagram. See, this is our Walsh diagram. This is for linear geometry. This is for bend geometry, right? So here it is sigma G plus sigma U plus pi U having same energy. Here it is A1, A2, B2, B1. So here it has some slightly less energy, right? Here it is written as B1 to E1. Okay, B1 to pi U. No change in energy as the MO remains non-bonding in both geometry, but B2 to sigma U plus here, okay, energy decreases as the end-on overlap of p orbital is more efficient and any terminal HS antibonding interaction is lost. Then A1 to pi U, rapid increase in energy as the MO goes from bonding to non-bonding. Then A1 to sigma G plus, the energy increases slightly as the terminal HS bonding interaction is lost. So here these are the reasons about this arrangement of uh, irreducible representations are the terms in the term of their energy. So here see the total valence electron in water is 8, right? So if you just put 8 electron, 2 electron, 2 4, 2 6, 2 8. So here it has same energy. Okay, so we have to assume the below one. Okay, so here 2 electron will be here. So in this case, linear and bent, the bent structure will be the right structure. Okay, because here see we have 8 electrons, so here we have to write 2 electron, here 2 4, here 2 6, here 2 8. Okay, but here at the top one the energy are same, so we can predict the right geometry. So we have to come to the this position. Okay, so the electrons present here, we can check that here it is pi U linear and it is A1. So it have higher energy, it have lower energy, and lower energy are always more stable. So the geometry will be bent, right? So it was all about your Walsh diagram. Thank you all.